Hello, hello. We are going to do some crazy schematics and power flow for DC motors now. Some of this stuff might take a few watches for you to really understand what's going on. Some of this stuff you might just realize that even though it looks like there's a lot of complicated stuff over on one side, you can actually simplify things down to the part that you care about and figure out pretty easily whether or not it's a wiring or electrical issue, or if we have an electronic solid state component that's gone bad. And these schematics are going to be what this week's quiz are based off of, and I've supplied another document that has clean schematics in there, but you're welcome to refer to this or the PowerPoint that has the power flow built into it to help answer those questions. So I hope that you use this tool to the best of its ability. So here is a power window circuit. This thing is old. This would be from early 90s, mid 90s. Most of our power windows now have at least some computer control because almost every car at least has one touch down for the driver's window. Some vehicles have one touch down and one touch up for all the windows. It's a mixed bag, case by case. But I want to start with electrical circuit first, and then we're going to get into more solid state and then computer control at the very end. So let's look at power flow here. The red lines are going to be power, the green lines are going to be ground, and we should also see that as current flows, once we actually close some of our switches and allow a pathway, that we're going to drop that voltage across our load, which our loads are the motors down here at the bottom for our power window circuits. So just isolating the driver's circuit all by itself, this one's obviously the simplest out of the four. When the vehicle is sitting there without a key in the ignition, no one's around, there is no power that makes it past this relay. It's not until we actually turn the key on, see this is hot all the time, but it deadheads at that switch. You turn the key on to accessory, right? So 2 clicks so that we can actually roll windows up and down or start the vehicle up. Then it sends current through the coil down to ground over here, which then closes the contacts and supplies power to my switch. And it also looks like it must go off, and if I had a moon roof, like a sunroof type situation, it sends power to that moon roof as well, so that would be able to move, which I guess the moon roof is like a window safety type feature. So here in its at rest state, right, I'm not actually trying to roll the window down right now, the circuits that go to the window motor are both attached to ground through my master switch. See this bus bar here inside, ground, and the switches are in their just upright neutral position because we're not acting on them. And the reason that they do this is we don't want a hot wire anywhere in the car unless it has to be hot. The window motors are in the doors open and close, and it's not uncommon to stress the wire out and have eventually the insulating coating wear off, and then the wire will even break. And what this does is it makes it so that we won't open up this circuit breaker at the top unless we have the door in the position in which metal is touching, which might be open, and we're trying to move the window up or down depending on which one of the two wires have gone bad, right? If we're trying to go up, this one would get power, and so if this one was chafed, that's when the circuit breaker would open, but then we'd be able to wait a couple of seconds and roll it back down again, which is kind of interesting. But I'm starting to get a little bit ahead of myself. So let's actually look and see what power flow looks like when this rolls down. So in the master switch, you see the arrow pointing in the down direction. Let's blow this up. Power is supplied here at this middle pole. We want to roll the window down, so I hit the switch and it moves this wiper, and you see the dashed line between the two showing that they're both connected, so they both move one notch to the left. We grab power with the circuit 333, and we grab ground with 334, which allows current flow to go through my motor in one direction, which will make my motor spin consistently in one direction, rolling the window down. When I go to roll the window up, here's my neutral position, and you can see both switches are going to move to the right this time because up the arrow is pointing to the right. Now my circuit 334 on the left grabs power, My circuit 333 on the right grabs ground, and current flows in the opposite direction, meaning that my motor will also spin in the opposite direction. We're just reversing polarity. Which side's power, which side's ground, which side's power, which side's ground, and the motor's just going to react accordingly. There's a video at the beginning of this week's lab that does a pretty nice job explaining that, and I recommend that you take a good look at it. Even though we did talk about DC motors when we did the starting circuits in the fall, I don't think that it was covered enough, and it's been a long time, so might as well. Let's make things a little bit more complicated. I'm going to roll the passenger front window down from the master switch. Now all of a sudden I've got this other switch in here, this other weird wire. Let's see if it actually really plays any effect in the way that the passenger window will work. So just like we were before, I've got ground supplied on both of these wires because that's my neutral position. I'm not pushing the button over here, so these are both in their neutral position, which just allows the wire to basically pass right through. And then the interesting thing is I've got this 170 circuit over here, and this supplies power to each of the individual window switches, so if I want to control the window from there, then I can grab power at that middle pole at that point. So, neutral, I want to roll down. Hey, it worked just like the driver's window did, because we're only using the master switch. Master switch has power, so it supplies the power to the window motor, and it also is the pathway to ground. So we flow that way. Now I want to go the opposite direction, neutral, and then I hit the switch, and now current flows in the opposite direction. At this point you might be thinking, hey, there's a circuit breaker up here and there's a circuit breaker down here as well. The reason they put circuit breakers into the individual window motors is because nobody ever rolled a window up and then believed that it was actually rolled up. They roll the window up and then they hold the switch for a little while longer, making sure it's up, or they're rolling up multiple windows at the same time. This circuit breaker just opens up. When this gets to the end of its travel, it turns into a short circuit because it has really low internal resistance. And so then this, just like a fuse would pop, it's a circuit breaker, so it opens for a time until it cools down and reconnects. And that just keeps us from overheating our switch and our wires. So just like some nice design from the engineers there. Thanks, guys. Passenger front down from the passenger front switch, right front switch here. So again, here's my neutral. We're grounded out, so everything's nice and safe, and the windows aren't just going to start rolling up and down by themselves. But now this time I'm going to control it down here. So my switch is down at the bottom. If I want to go down, you can see that power flows in the same direction it would have been if I used this switch, except for I'm just cutting this part of the circuit out of the equation. I have power supplied through my lockout switch, my child safety switch. It's like, hey kids, stop playing with the windows, and you turn power off to all the switches back there. And then the same thing will be true when I go to roll the window back up. Power flow will be very similar. There you go, I grabbed it with this switch, and current's flowing the opposite direction now. Neat. Switches at rest, not locked. And so this is a look at what this system would be like if we're just cruising down the road, no one's playing with any of the windows. And then if the kids start messing around with the windows in the back and I want them to cut it out, I can kill power to their switches, but I still have power in the driver's seat, so if they rolled the window down and I don't want it down, I can roll it back up again. Or if one of them farts and I want to get all that fart out, then I can roll the window down and make them deal with all the wind and the noise. Alright, so watch this as many times as you want to. I also supplied the PowerPoint that has these animations in it. You'll have to put it into the actual slideshow, like start a slideshow, to be able to see the power flows change, but spend time with it. It becomes pretty simple. You start realizing, like, oh, I'm just putting power and ground this way, and then the other way, current flows one way, current flows the other way. It's not that complicated, but when a lot of people look at a diagram like this, they just get overwhelmed by the number of wires and switches and stuff in there. So dumb it down. The reason why I painted this with the colors there, it's because one of the first techs that was a real mentor to me, great tech, did a really nice job with electrical diag, but every time he went to diagnose a problem, he'd print out the diagram, and then he had a bunch of color pencils, in his toolbox, and he would go and he would do this. He would be like, okay, I only care about this circuit. So let's go all the way back. So I only care about this circuit, and the power window doesn't work. So we'd go through and he'd color like, so this is where power should be, this is how it should be grounded, or it won't roll down. So how should it be set up? Okay, now it's really simple. All I need to do is make sure I've got power here and ground there. And if I do, then the only thing that could be wrong is the motor at that point, right? So any tool in your toolbox is useful, even if it's just a color pencil. All right, so now we're going to get into something that looks a little bit more hairy. So this is a 2010 Toyota Camry, and we're going to deal with a power wiper system. Here's my wiper motor down here. Here's my washer pump up here, and then here's the actual switch on the steering column right in this spot. So as we take a look at this, there are some parts that are a little bit complicated, but don't get overwhelmed. Be patient, and everything will work out just fine. Inside of this switch, you can actually see a couple of transistors, which is the topic of the week this week. And just another look at our NPN versus PNP transistors. If you have not done the lab, or if you have not watched the PowerPoint that deals specifically with transistors, I'd recommend you go take a peek at that real quick, because I'm going to assume some prior knowledge in the rest of this PowerPoint. So here's power flows off. Remember, red being power, green meaning ground. And down here, well, let's zoom in here first. This switch setup is different. This is more of an Asian style diagram, being Toyota. And all this means is when I'm off, I'm connecting this circuit, see the little circle, with this circuit right here. Or this circuit with this one. Okay, so they're just showing that the switch connects these wires together, which is what switches do. They connect wires together. So what's happening, we'll go down here, is I've just supplied ground to my motor. I've got a couple different brushes. This would be considered a shunt motor, but it's talked about inside the video for how a DC motor works. And you can see I've got 3 different brushes. I've got one dedicated ground brush. This is always going to be ground. But then I've got this brush off at a 90-degree angle and a brush opposite at 180 degrees. This is my low speed. You see how the brush isn't lined up in the way that we could get the motor to spin the fastest possible. This is my high speed. 2 brushes apart from each other by 180 degrees are going to give a torquey and powerful motor. And the reason why they create a shunt motor here, which means that I've just got current flows through the field coil first, creating the magnetic field around the armature of the motor, and then through the armature itself, is it makes a motor that spins at a very consistent speed, which sounds really nice when I get to wipers. I either want it to wipe slowly, or I want it to wipe fast. But I don't want it to be like, yep, right, okay. We've talked about the things to talk about. Down here, there's this weird switch. This is the park mechanism. So when you are wiping your windows off when it's raining, nobody wants to have to time it perfect so that when the wipers are down, you're like, oh, I gotta hit off right now, or the wiper's gonna get stuck in the middle of my windshield and make it hard to see and all that kind of business. So they add this mechanism so that when the wipers are down, the switch would be in this position, right? Because all diagrams are drawn with vehicles in their at-rest position. But if I shut off the wipers while they're halfway through their travel, this switch is going to be connected to this wire until the wiper comes all the way back. And we're going to see what that looks like right now. This is called parking. And so here I was off. Let's say my wipers were in the middle. And this would happen even if I turned the car on. Like, let's say I shut the car off, the wipers are in the middle of the windshield. I don't care. I get in the next day, turn the car on, it's sunny outside. It's going to park the windows, and it's going to allow, because of this switch right here, it's going to send current through here. And even though my switch is off, right, and it's connected just like that, it sends power to this field coil and the brush until the wiper motor comes around and the switch comes back down. There's actually something mechanical physically that pushes the switch one way until the motor comes to that sweet spot and the switch has pressure released from it, just for like a very, very small amount of travel. So I would say that while the wipers are spinning, or while the wiper motor is spinning and the wipers are wiping back and forth, this switch is connected to this circuit the majority of the time. When it's turned off, obviously, the switch is going to be connected to ground. All right. So low speed, that one's easy. So here's low here in this diagram, and what we're doing is connecting this wire and this wire. All right, and if we look, let me do that again. If we look, this wire hooks up to this pink wire here, which goes to my low speed brush, convenient. And then this wire connects to this like teal blue wire, and that is supplied power by this fuse. So that's all that happens. Low speed, okay, boop, put it to the low speed field coil and the brush, and we're off to the races. Slowly wiping. It's not raining that hard. When I go to park it and I turn off my wipers, well, then my park circuit engages, and still that's going to be through the low speed brush, and that is going, part of the reason why they make it through the low speed brush is they use this for like the washer function as well, but also so that it's not moving so fast that maybe momentum causes us to travel past that park position and the wipers would continue on traveling. Not likely, but possible. High speed? Yeah, high speed. Here's high speed here. You can look at your schematic, or here, I'll zoom in for a half second. Hey, look, hi. So what this does is now I'm connected to this green wire, which comes down, and there we go. That's our 180 off brush. So that's our high speed brush. And again, my teal wire down here, which is supplied power by this fuse up here. So now I've put power through my high-speed field coil, which that's not really going to be any different than the other one. Like the two coils are just making magnetism around the motor. But now my brushes are lined up so that the armature is tuned, basically, to spin it as fast as possible, which is real nice because sometimes it rains really hard and I want the water to go away fast. When I go to park, that park circuit's going to be the same, and we revert back to that low-speed circuit. Intermittent, now this becomes a little bit interesting, and what we have to do is take a look at the inside of all this craziness going on in this switch at this point. The real culprit here, the thing that really makes this whole work, or actually it's a few things, is one, I've got this PTC thermistor, so PTC, positive temperature coefficient. As the heat of that resistor goes up, the resistance value goes up as well. When current flows through a resistor, heat is created. Right, we're taking electrical energy, turning into heat energy. That's how we resist current flow. In here, I also have an NPN transistor, a PNP transistor, and a relay. And this relay is kind of hard to see, but here's my coil. And what it's showing through this dashed line is it acts on this switch. And what it'll do is it'll pull this switch up to this contact and supply power, which is coming in through that teal wire that goes up to the fuse panel. So intermittent stopped. Intermittent's just, it wipes once and then it stops. And it wipes once and it stops. And oftentimes when an intermittent wipe is going on, you'll actually hear a relay under the dashboard give a click. In this case, the relay is built into the wiper switch assembly on the steering column for this vehicle. And what happens is this relay is really, really important as far as allowing the wipers to start. We're in our parked position, so I'm attached to ground down here. So I need something to get the wipers to move a little bit so that then the parking circuit can take over and complete the wipe, and then we'll wait for the wipers to get nudged a little bit again. And this PTC thermistor is the whole ball game as far as that's concerned on what the little timer mechanism is. So I'm stopped because my PTC thermistor got so warm that the resistance became so great that I didn't have enough current to bias this transistor, NPN on the ground side of my coil. So this transistor right now, because there's not enough voltage and current here to make this thing allow the larger current to flow, well then the relay turns off, and this is just connected to ground right now, so nothing's happening. We wait a couple seconds, right, the pause between the wipes. This cools down, and this is supplied power all the time. So this cools down enough. Well, let's take a step back. This is supplied power all the time, but it is not supplied ground all the time. Okay, you see that we have to get the resistance here has to decrease to a certain point at which it will allow enough voltage and current to bias this. And the way that that happens is this has to cool down. And the only way this is going to cool down is with a little bit of time of no current flowing through it. So it wipes, it nudges it, it gets warm. It's like, I'm hot and it's too much work. I'm not going to do anything right now. No current gets to go by me really anymore. And the relay turns off. The park circuit runs and allows the full wipe to happen. By the time it's come back, this thing is starting to cool off. My voltage on the ground side of this is building. The current flow flowing through it begins to increase to the point at which I can actually flow enough from my base to my emitter to allow my higher current to flow from the collector to the emitter. And then my relay's coil turns on. It pulls this switch up and supplies power to it, and the wiper goes off again. So here we are stopped. Here we are restarting. You can see that how the voltage has changed now in here. We had dropped everything across this where we just had ground on this side, but it had cooled down to the point at which it allows some substantial current to flow. And there's enough voltage here before the last little resistor that this biases and allows current to flow through my relay coil, which pulls my switch to that hot pole, nudges the wiper off of this park position, and then the park circuit takes over. So let's take a look at that again. It stopped. PTC thermistor needs to cool down. Alright, it cooled down enough, the relay clicks, it nudges the wipers, the PTC thermistor gets too warm. You can see the voltage just dropped back down again. And now my park circuit, which has been parked for everything so far, takes over, and that's what actually completes the wipe on this circuit. I know, it's kind of crazy, it's pretty intense, but it's worth understanding. Like, look, we've built up this basic knowledge of resistance and current flows and voltage drops, and then into semiconductors where we're understanding how diodes are working. You can see the diode and the Zener diode here, how they're working, and then the fact that this transistor and this PTC thermistor, which is also semiconductor, as the temperature increases, the resistance increases really, really rapidly. We're seeing as we're adding all of these bits of information together, now all of a sudden I understand how this circuit works. I had to spend some time really tracing this through, but I think it's pretty rewarding to understand, well, I can pretty easily tell you whether or not this motor's any good. Does it have low speed? Does it have high speed? Does it park? If it does all those, it's not the motor. So I can move away from that. Like we're saying, the customer comes in with an intermittent wiper in-op issue. Then I can look at the switch and be like, golly, there's a whole lot of stuff going on inside of that switch. Oof. Well, if the wiper motor's good, is there a circuit that's specific just to that switch? Let's see. That makes it so we have intermittent. This wire's for my low speed. Or actually, this wire's for power end of the switch. So if any of the other speeds work, it's nothing wrong with that. This wire's for high speed. See how it goes to the high speed brush. This wire's for low speed, and park for that matter. So if it has low speed, we know that's not the issue. The park function is built into the wiper motor. So unless like something over here burned up in my off, like this piece right here, then I would still have park. And so it limits it. It's like, well, I know it's not the motor. I know it's not a bunch of these freaking wires over here. It could potentially be this wire that goes to ground over here. I'll give you that much. All right, but what the pinpoint test would tell you to do for this would not be, look at the diagram and do some electrical education on how transistors and discrete circuits work. It would say, do you have power, or do you have ground here? Do you have power on this wire? Ohm out these wires. Do you have low resistance? Okay, well then it has to be the switch. That's exactly what it would do, because it knows not all techs are going to be able to look at this and make heads or tails of it. Hopefully, eventually, one day you'll be able to look at this and make some heads or tails of it. You can look at the pinpoint test, realize, okay, it just wants me to ohm out wires, basically. Look at this, and then maybe use your big boy thinking cap and figure out what's going on. That's my goal when I teach this class, and that goal has been much harder to achieve this time around, but hopefully you're still getting something meaningful out of it. All right, on to something easier. When I want my washer to wash, I've got my washer motor up here, so power comes in, and then this is the only load, so it should drop it. And you can see how it comes down into my switch, and then here's my ground circuit out of the switch right here. So it should be power, and then the rest of it's just ground because I dropped it all across that motor. And at the same time, there's a missed function in my master switch. And this is again just my low speed circuit. If you compare the two, low speed connects these two wires. Hey, look, mist connects these two as well. But it also, you'd have to pay attention, it connects that for the washer as well. Hit the washer, it sprays the windshield, goes into the mist function, and you get a wipe out of it. Pretty fun. Wipes as long as you're holding the button down from the looks of things. Alright, so we've looked at electrical, we've looked at a solid state electronic circuit. Now and these are all the connectors that would be associated with it. You can look back into this diagram and it actually tells you at these different junction points what connector numbers you're using. So if you wanted to look at that, I think it's pretty beneficial. But then let's take a look at a computer-controlled electronic circuit and understand how a lot of people get frustrated. Oh, computers, they make things really complicated and hard. No, in this one, this is the easiest diagram to understand what's going on in. So here's my master window switch. Here is my left front power window motor. This is a computer. You can see how it output controls the motor, but this is showing that it's all part of the same assembly. And then there's a box in the box, which means don't pay attention to the man behind the curtain. This is a computer over here. I've got battery power and another power coming in. So this, I bet, is hot all the time. Yeah, so this one's hot all the time, and then this one is an accessory delay. So it needs power and another power. This one's probably power for the motor, and then this is power for the logic of the module. It needs both of those to actually turn on this computer, and then ground supplied all the time, because why not? Ground's great. So when I want my window to go up, I'm going to hit the switch in my master window control switch, and if you look at this, here's my up circuit, pretty clear. And it's showing that when I hit the up button, let's trace this real close, maybe I'll zoom in, it's kind of blurry, but it's showing when I hit the switch, this is normal, so I'm not hitting the switch now, so when I hit the switch it'll move it, and this is going to grab power. So this has a resistor in it, so it's not going to be all of battery voltage. And then this over here, when I hit auto, see how these two are connected and these two are connected? So when I hit auto, I'll go this one first, and then there's the next button, right? It goes boop, boop. And then, then this one, and that would connect to power over on this other wire. They put this resistor here so that if I get a short to ground on this wire, I don't have to worry about anything. If that happens, this is the only resistance. It drops all the voltage. Everything's safe. Okay? Good talk. So when I want to go up, the module is going to see voltage on. I don't know what I've done. There it goes. So when I want to go up, it's going to see voltage on pin 3. right here of connector 524. And you can see that's the only connector that goes into this, 524, 524. So these are all part of the same connector. So when I want to go up, I get voltage there. That's all this module needs to see, along with being supplied 2 legs of power and ground. It's all it needs to see to roll the window up. And that's just normal. As long as I'm holding it, it's rolling it up until it gets to the top of its travel, and then it might have a circuit breaker or something of that nature. Maybe a position sensor, and it just limits it. When I want to go down, guess what I'm going to get on my down circuit? Battery voltage. Whoa, this is pretty simple compared to all this other stuff. One touch up, I will see power on my up circuit first, followed a brief time later by power on my down circuit. So basically, if it sees power on both these circuits, it's going to pay attention to which one did I see power on first. So that's going to tell it which way to go. If I see it first on the up, then I'm one touch up. If I see it first on the down, one touch down. Crazy simple, huh? Let's look at our relay. I know we're masters of this, but I did it anyway, so might as well do it. Relay off. I would have available voltage at pin 3. And because there's no current flowing, because my little NPN transistor in this microprocessor is in the off position, I would actually see available voltage all the way into this because there's a disconnect between my power side and my ground, and it's not until here. No voltage is dropped across this relay coil because no current's flowing. Think about Ohm's law. To solve for voltage, I needed to know resistance and current flow. Current flow is 0. So what's 0 times, let's call this 50 ohms, 0 times 50, 0. So I have 0 voltage drop, so I would have available voltage right there. Relay turned on, microprocessor grounds out that relay. I drop all my voltage across it, so this is ground side now, and then voltage is supplied to here. Doesn't matter if my relay's on or off to supply it here, because this little splice guy up here supplies power here, and then all the way down this red wire. So that should have power no matter what state my body control module has things in. That ends it. I know this was a lot of information. Go watch it again. If you still don't understand a part, watch it again. If you just go through it a few times, try to make sense of it, this will start to happen. The only way you're going to learn this stuff is by repetition, over and over and over again. Your brain's actually growing. Take the time to let it grow. Think about it. You didn't become great at shooting baskets by doing it one time and then being like, all right, I'm an expert of it now. Obviously, I'm not any good at basketball. I don't really like it very much, just be honest. I didn't become good at electrical by being like, I've looked at a diagram, now I am incredibly good at electricity. No, I did it a bunch of times. Then I did it some more, and I'm still doing it. So this is the only way it's going to happen for you. Don't be bashful about it. This is the way that learning goes. All right. Hope you had a good week, and I will see you next time.